Tomorrow is the June solstice. That's summer for us northerners, winter for those down under. In honor of this momentous occasion, and really just as an excuse to get out there and flex our observation muscles, let's get out there and do a quick observation. I'll put a link to the original video up there where I describe what we're trying to accomplish and how to do it, how to participate. And down in the description, there will be a link for the Google form where you can submit your data and participate with the rest of us. In the previous couple of videos, I went over how this all works with protractors and with math for the flat earth version. Let's look now at how the globe version works and how the globers can participate. Now, if you're not a glober, if you're on the flat side, this video we'll go through what the globers think is going on and how we are going to apply our measurements towards that. I think there might be some learning in there that's valuable for you as well, or at least some stuff for you to comment on, particularly at the end. So what is it that we're going to do? We're all going to be doing the same experiment. We're all going to go out at local noon your time on either the 20th or the 21st. I'll also accept the 19th or the 22nd. And we will put a stick in the ground pointed straight up. And right at local noon, we're going to measure the length of the shadow. From that, we're going to get the angle to the sun. That's the sun that's casting that shadow. So the angle to the sun can be gotten by simply measuring your stick and measuring the length of the shadow. Just like I showed in the previous video, that's the tangent of the angle, and with an arc tangent, you've got the angle. If you looked at the previous videos, you saw a diagram very similar to this, where we imagine that the ground is flat, and in two different locations, we are going to measure the angle up to the sun, and using that, we'll figure out where the intersection is. However, the globe Earth hypothesis suggests that the sun is very, very far away, and so that these lines should actually be parallel. In order to make those lines parallel, we have to imagine that the ground must be curved in some way. Perhaps it's not straight. So what might that look like? Something like this, where the rays are actually parallel, but the angles of the observations are different, and that is caused by a curvature of some kind in the surface. So the surface is not flat, it's got some curve to it, and that could be what explains these different angles. What we need to do then is to work out exactly what sort of curvature can cause that. Now, the hypothesis is that it's going to be roughly spherical, but let's not assume that. Let's actually see if we can't deduce that from these measurements. How would we do that? The first step is to figure out how much did I have to rotate this angle in order to get it to be parallel to this other beam. Here we see the two parallel lines having been brought together, but these are in their rotated ground. This is the ground angles. How much did I have to rotate that green one in order to get it to be parallel with the purple? So the angle that I had to rotate the ground in order to get these two angles parallel, we can see, I think, is this angle right here. And that angle we can express as simply alpha 1 minus alpha 2. In order to parallelize those rays, the ground must be curved in such a way that the ground's angles are different by alpha 1 minus alpha 2 at those two different points. Furthermore, we're going to work out the distance between those 2 points, and so we will know now that those two measurements were taken along a surface distance of d. Let's see how we can combine these two different measurements to deduce the shape of that curvature. We are not going to assume anything about this curvature. We are just going to say there must be some kind of curvature. It could be concave, it could be convex, It could actually be flat. That would be a flat curvature. Maybe it's concave in some places and convex in other places. Hard to say. What we'll do is treat the surface as a series of arcs. Each segment between measurements we will model as a section of a circle, an arc. And then by linking those together, we will create a diagram of what the overall shape appears to be. Here's how it works. We'll take our first pair of observations, and let's say these are the two observations here, and these are the angles. When we subtract those two angles, that creates this arc in here, and if we know the distance between them, we can now work out what is the radius of this small section of curvature. So using this simple relationship that d1, the distance out on the outside, is the radius times the angle, and I'm converting it from degrees into radians with this, that will give us what is this arc length on the outside. Now let me stress, because this is something I don't think many of us have really done. Let me explain what I'm doing. I'm creating an unknown curve by treating it as a series of arcs. I have drawn the diagram as if the arc curves this way, but depending on the sign of this difference, it could curve the opposite, and if the difference is 0, then it would be completely flat. What I'm going to do then is I'm going to link up a series of these arcs to create the overall shape that we observe it to be. So this little section here appears to be, according to this diagram, an arc of radius r1. And we will solve for r1 right there. That's the formula that we're going to use to create that segment. And then what we'll do is we'll take the next observation down the line, as say at this location, and maybe it's got this angle. We'll do that same thing and measure the radius of the curvature at that point. And we'll go again, and we can now subdivide this whole range that we have observations into a series of sections and find out what sort of shape that is. There have been a few complaints in the comments from some globe skeptics who don't have a lot of faith that the observations that I have described can do what I'm claiming that they can do. And so I'd like to take a moment to address those now. First up, have I assumed that it's a sphere? No, I have not assumed that it's a sphere. We have imagined that we have an unknown curvature of unknown type, and we are going to chop it up segment by segment, and at each pair of observations we will use the difference of the angles to tell us what sort of curvature we appear to have, whether it is concave or convex or even flat. And we will then line up those measurements section by section and come up with the overall shape of what we appear to be living on. Next up, have I assumed the radius? No. I have not assumed the radius. We are going to take the angles of the light and the distance over land between those 2 points, and from that we are going to calculate the radius of each section again. Okay, have I assumed 111 kilometers per degree of latitude? Well, yeah, not really, because as far as I know, we all agree to that, and that's not under any kind of argument. I mean, as far as I know, if you want to argue that that number needs to be validated, then maybe we should make an effort to validate it. I think that should not be that hard. We will absolutely go and use Google Earth to measure the distances between the things and verify that it is coming out as 111 kilometers per degree of latitude. Okay, next up, have I assumed the sun is a physical object? I get a lot of complaints about that. The sun is apparent. The sun is not physical. So what? This works for any light source. I did it with my flashlight. but I'm not touching the flashlight. I'm just looking at where the light of the flashlight is coming from. And this will work for any apparent light source. Any light source that shines out rays and casts shadows, which is any light source, you can do this. This is, and let me stress, we are not measuring where the physical object that generated the original light is necessarily. We are measuring where the light appears to be coming from. So if the light, for example, if light is bounced off of a mirror, then you can still do this. You're going to get where the light appears to be on the other side of the mirror, not where the light physically is. Understand? So we are not assuming any physicality. It's not necessary. And we aren't necessarily determining where the sun physically is. We are determining where the sun appears to be. Okay? I think that's pretty straightforward. Finally, have I assumed that the light from the sun traveled in straight lines? Yes, actually I have. We are assuming that. That's good. And so ultimately I expect we'll circle back on this after we have our observations and we find what we find. We are going to have a discrepancy in one of the models. One of the models is going to work out pretty good, and one of the models is not going to work out very good. If you're curious about why I'm saying that, it's because the math says that these two predictions don't match up. So if we do a good job, the two predictions can't match. So only one of them can really be truly successful. So when we come back here and we're looking at our results, at least for one of the sides, the question will become, did the light bend? How much did the light bend? Okay, that's what we're going to need to come back and talk about. A lot of people are preemptively generating a lot of comments about light must refract, and there's clouds, and there's some other reason why the light does not travel in a straight line. Most of the comments don't put it that clearly, but I'd like to encourage everyone to think about this, that the complaint is, it can be boiled down to, did the light travel in a straight line? All of my diagrams are based on that principle, that the light came in a straight line. But we know that there's refraction. We know that that's a thing. I mentioned it could be reflection, it could be refraction. Who knows? What I would like everyone to do is to step back from the idea that this is a globe proof. This is a flat earth proof. This is not a proof. This is an observation that we're going to do collaboratively. And the way we should be looking at this is not, is this going to finally shut down those nasty globers? No, this is the wrong way to look at it. What we should be looking at is, how much did the light bend? If you're worried that these observations are not valid because I did not consider refraction, I would like to ask you, instead of trying to shut it all down, let's use that as a jumping off point to learn how much refraction is there. I think what I'm trying to say is, instead of coming here and commenting, this can't work because you didn't account for refraction, let's just turn that around and say, hey, that's a great way to measure the refraction. Okay? And we can then come back here with our observations and say, hey, it turns out, maybe it's going to turn out that it's not a perfect globe, and the only way we can fix it is if we add refraction. And if we do have to add refraction like that, how much refraction and in what places do we need to add? How much everywhere? How much up there? How much down there? To get this thing corrected. We can do the same thing for the flat. And then we'll come back with that, with having learned something new. We don't have to reject all of our previous ideas and our tightly held belief systems in order to learn something new. So I'm looking forward to seeing observations from many different participants. And let's come back here and not treat this as an excuse to attack one another and prove that our models are wrong or that our models are right, or that the other guy is a fool or anything like that. Let's come back here and use this as a data set from which we can make measurements about those unknowns that we still have. Okay? All right. Looking forward to it. See you out there tomorrow and the next day. Happy solstice, everybody.